Chapter 20, the Electron Transport Chain. Let's look at the big picture again. In Chapter 19, we learned that the acetyl-CoA produce high-energy electrons through citric acid cycle, also called TCA cycle or Krebs cycle. And the high-energy electrons are carried by electron carrier NADH and FADH2. This high-energy carrier flow through the electron transport chain and reduced energy produce ATP. The Chapter 20 talk about the electron transport chain, the stair, and Chapter 21 is how the energy released from ETC are used to produce ATP. Chapter 20 outlines. First, we learn oxidative phosphorylation take place in mitochondria. Then we're going to learn oxidative phosphorylation depends on electron transfer. Third, the respiratory chain consists of proton pumps and a physical link to the citric acid cycle. Oxidative phosphorylation captures the energy of high-energy electrons to synthesize ATP. The flow of the electrons from NADH and FADH2 to oxygen occurs in this electron transport chain or respiratory chain. This hexagonic set of redox reactions generate a proton gradient. The proton gradient is used to power the synthesis of ATP. We're going to learn in details in Chapter 21. Cellular respiration is a metabolic pathway that breaks down glucose and produces ATP. The stages of cellular respiration include glycolysis, Chapter 16, pyruvate oxidation, Chapter 18, the citric acid and Krebs cycle, Chapter 19, and oxidative phosphorylation, Chapter 20 and 21. Let's look at another big picture and review what we have learned. In Chapter 16, we learned glycolysis pathway. Glucose break down to 2-pyruvate, produce ATP and NADH. This pathway happens in cytosol. Cytosol is the liquid portion of cytoplasm. In aerobic condition, the pyruvate enter the mitochondrial matrix and undergoes the oxidation, pyruvate oxidation. Pyruvate lost one carbon in the form of carbon dioxide and combine with CoA to form acetyl-CoA. The acetyl-CoA then undergoes the citric acid cycle. We learned that in Chapter 19 and produce ATP and NADH and FADH2. NADH and FADH2 are high energy electron carriers. These electrons, together with the NADH produced from other pathway, are all entering this electron transport chain, which is a set of embedded intermemory protein complex. While passing through this transport chain, the electron gave the energy an electron to oxygen, and the energy released through this process are used to produce ATP. And this electron transport chain and later the ATP synthesis are together called oxidative phosphorylation. The oxidative phosphorylation in eukaryotes takes place in the mitochondria. The electron transport chain and ATP synthesis occur in the mitochondria inner membrane. The inner membrane is the site of electron transport and ATP synthesis. While the citric acid cycle and fatty acid oxidation occur in the matrix. This is a photo of mitochondria. You can see that the mitochondria has double membrane. There's an outer membrane, there's an inner membrane. In between the outer and inner membrane is intermembrane space. And this intermembrane space is where the electron transport chain and ATP synthesis happen. The electron transfer potential of an electron is measured as redox potential. The reduction potential E0 or redox potential is a measure of a molecule's tendency to donate or accept electrons. A strong reducing agent readily donates electrons and has a negative E0. A strong oxidizing agent readily accepts electrons and have a positive E0. The standard free energy change, the delta G, is related to the change in reduction potential, and the relationship is a reciprocal. Did you know an oxidant is the acceptor of electrons in a redox reaction, while a reductant is the donator of electrons in a redox reaction? This table is a standard reduction potential of some reactions, assuming the oxidant receives 1 electron turned to reductant. Let's look at this one important reaction from NAD plus receive 1 electron turned to NADH. The delta E0 is negative number, which means the delta G would be positive. So if NAD plus receiving electron to become NADH is a positive, has a positive delta G, then from NADH to donate an electron turned to NAD plus would be a reaction with delta G has a negative number, which means is that NADH turned to NAD plus is a reaction that releases energy. Energy is released when high energy electrons are transferred to oxygen. Let's look at the reaction. When NADH donate electrons to oxygen and reduce oxygen to water, that reaction has the delta E0 1.14 V, and that's calculated as a delta G, the free energy is minus 220 kilojoule per mole. That's a substantial large energy release. We know for synthesize 1 ATP, you only need 30 kilojoule per mole. So this energy can produce numerous ATP. And the energy is used to establish a proton gradient and later be used to synthesize ATP. The electron transport chain is composed of 4 large protein complexes. The electrons donated by NADH and FADH2 are passed to the electron carrier in the protein complexes. The carriers including flavin mononucleotide, FMN, iron associated with sulfur in proteins, iron-sulfur proteins, iron incorporated into heme that are embedded in proteins called cytochromes, and a mobile electron carrier called coenzyme Q. Let's look into one of the electron carriers inside the protein complexes, the FMN. You can see this molecule has 2 activate sites. When FMN receives electron, one electron's accepting site is here, another electron accepting here, and this FMNH2 receives 2 electrons, carries 2 electrons. This is the same as the FAD. We learned that in the past. Let's examine how electron flow within the complexes in the inner mitochondrial membrane, which generate a protein gradients. These complexes appears to be associated with one another in what's called the raspersome. The electron flow down a energy gradients from NADH to oxygen. It's arranged so that the electron always flow to more positive reduction potentials, a higher electron affinity. The flow is catalyzed by 4 protein complexes. Complex 1, NADHQ oxidoreductase. Complex 3, Q cytochrome C oxidoreductase. 4, cytochrome C oxidase. And complex 2, succinate Q reductase. Iron is a component of all the complexes as well as a cytochrome C, which links complex 3 with complex 4. The respiratory chain consists of proton pumps and a physical link to the citric acid cycle. Electrons flow from NADH to oxygen through 3 large protein complexes embedded in the inner mitochondrial membrane. Last slide, we introduced 4 large protein complexes. 3 of them are embedded in the inner mitochondrial membranes. These complexes pump protons out of the mitochondria, generating a proton gradient. The 3 complexes are complex 1, NADHQ oxidoreductase, complex 3, Q cytochrome C oxidoreductase, complex 4, cytochrome C oxidase. And in addition to the above complexes, the complex 2, succinate Q reductase, delivers electrons from NADH to complex 3. Succinate Q reductase is not a proton pump. The complex 2 introduces electrons from NADH to the chain, the transport chain, while complex 1 introduces NADH, the electrons from NADH. Let's look at the electron transport chain again. We can see the NADH introduce electron into the chain through NADHQ oxidoreductase. Well, the succinate Q reductase introduce electrons from NADH into the transport chain. And see on the left that the potential, the electron affinity start with some negative number all the way down. The electron affinity is increasing down the chain. The complexes shows in yellow box, which is complex 1, 3, and 4, are proton pumps. Well, the succinate reductase, the complex 2, is not a proton pump. Let's look at the beginning of the electron transport chain. The high potential electrons of NADH enter the respiratory chain at NADH-Q oxidoreductase. The electrons from NADH are passed along to Q to form QH2 by complex 1. QH2 leaves the enzyme for the Q pool in the hydrophobic interior of the inner mitochondrial membrane. 4 protons are simultaneously pumped out of the mitochondria by complex 1. Let's look at the second complex in the transport chain, the complex 2. Ubiquinol is the entry point for electrons from FADH2. The succinate dehydrogenase of the citric acid cycle is a part of the complex 2, the succinate Q reductase complex. The FADH2 generated in the citric acid cycle reduces Q to QH2, which then enters the Q pool. Coenzyme Q is frequently marketed as a dietary supplement, often called Ch20. There are many health benefits being claimed for this supplement, like boosts energy, enhance the immune system, and also act like a antioxidant. There's evidence start to show that COQ supplements also maybe benefit people undergoing severe physiological stress. However, no studies have established that COQ supplements will help a well-nourished person in any activity. Let's look at what happened at the complex 4. The Q cycle funnels electrons from a 2-electron carrier to a 1-electron carrier and pump protons. The QH2 carries 2 electrons, while cytochrome C carries only 1 electron. The mechanism for coupling electron transfer from QH2 to cytochrome C is called the Q cycle. In one cycle, 4 protons are pumped out of the mitochondria and 2 more are removed from the matrix. You can see 2 protons needed for the reaction, 4 protons produced at the inner memory space. Let's look at what happens at the end of the transport chain. At the end of the chain, oxygen is reduced to water. The cytochrome C oxidase accepts 4 electrons from 4 molecules of cytochrome C in order to catalyze the reduction of oxygen to 2 molecules of water. In the cytochrome C oxidase reaction, 8 protons are removed from the matrix. 4 protons, called chemical protons, are used to reduce oxygen. In addition, 4 protons are pumped into the inner intermembrane space. Let's put things all together. In chapter 19, we learned that acetyl-CoA enters a citric acid cycle, produce high energy electrons carried by NADH and FADH2. The NADH enter the electron transfer chain through the complex 1, and FADH2 enter the electron transfer chain through complex 2. The electrons flow down the transport chain and eventually, at the end of the chain, transfer the electrons to oxygen and reduce oxygen to water. Meantime, the three proton pumps, which is complex 1, 3, and 4, all pump proton outside the mitochondrial membrane, which create a proton gradients. In chapter 21, we're going to learn that the proton gradients will be used to synthesize ATP.